is the second lecture on the effective theories for dark matter. Before we start, I should say that everybody that was able to get here this morning after yesterday's dinner should get a prize, or at least had a chance for a prize. So here we go. Here we go. So I have two props here. So the first one is I bought candy from the local supermarket. It's the best looking one. I don't know if it's any good. It's frutas, they are gone. So the rules are, whoever asks a question, you get a candy, or if I'm more precise, I will throw candy at you. So it's either you get a candy or at least the person next to you wakes up. However, there's also a second prop. Oh, I should say there's no stupid questions. No, there's no stupid questions. However, there is a second prop, which is the rock. Yes, was there a first question? I guess not. All right. So what I do is I review the rest of the what we did yesterday. So first lecture, we started with the EFTs in direct dark matter detection, and then that means we focused on dark matter scattering on nuclei, and we had two EFTs, two versions, one with nucleons, and these coefficients were functions of the momenta that flow through the interaction, and then there was another version where we had couplings to quarks and gluons, and these Wilson coefficients are constants. So now what we need to do today is we need to finish dark matter scattering on nuclei. So this will take us maybe up to half an hour, let's say. And then we'll connect to higher scales. We'll do the loops. And then we'll switch gears completely. So I just pick two examples for special EFTs. It has little to do with what we did so far. So we'll take a heavy dark matter limit well above the electroweak scale. And then it has renormalizable electroweak interactions, and let's see how you deal with that. And then finally, I have an example where the EFT breaks down, which will be dark matter production at the LHC, and how you fix this with the simplified models. All right, so direct detection. All right, so we were dealing with this tower of EFTs. So that's the UV theory, high up, above the electroweak scale, so we assume there is a gap there. And then there are steps. In the first step, we integrate out the mediators, and we were dealing with these effective field theories at low energy, down there. And as I said, so there were these two choices. One had non-relativistic nucleons, and the other one had dark matter coupling to quarks and gluons. And we asked the following question. So if I have a formulation where I have dark matter coupling to quarks, how do I go and connect to the non-relativistic theory with nucleons? And we did quite a lot. No? So I had this slide where I said what we want to learn. So there were general lessons that were promised. So first one, that scarily leading contribution is due to dark matter scattering on a single nucleon current. That we did, no? We suffered through many details, and we ended up with the following statement, that dark matter will scatter on one nucleon. If I look at the contributions where I have point-like interaction with two nucleons, this was parametrically heavily suppressed, and then for some contributions, this I did not show, but if you apply the same formula, right, the same counting formula, it takes a little bit more work, so I can't do it on the slides. You will find that the first correction would be, for instance, for scalar couplings, would come from a pion exchange, and it's only suppressed by 1 power. 1 power is not that much, it's tenths of percent. No? So Maybe you're expecting 10, 20, maybe even 30% correction. What we'll do today will show that not all non-relativistic operators are generated, and actually in the next few slides I have a few examples where we understand that switching just one non-relativistic operator at a time is not justified when you do an analysis. Alright, so let me just finish the matching, so this non-perturbative matching that we're doing from quarks and gluons to nucleons. So what happens, so now we have the two, so we have this heavy baryon chiral perturbation theory, and this will describe me how, for instance, if I take a vector current on the quark side, I will get a nucleon current, where this is a 4 velocity of the nucleon. And then if I have an axial current, I'll get a spin operator, and all this is now described in this heavy baryon formalism. So this is now, I mean, I'm just showing roughly how it goes. You also have a hadronization in terms of the meson current. So the same quark current will also give you a current where I have pion fields. If I have a vector current, I will have to have two pion fields because of parity. Pion are pseudoscalars, so in order to have the right parity, which will come from the derivative, I have to have the rest to have a positive parity. The axial current will have only one pion in a derivative, and so on. So now we apply our counting, and you find the following. There are two types of leading order diagrams. So the leading order diagrams have dark matter scattering only on one nucleon, but this can happen in two ways. So it's either I have a point interaction, so this will happen for vector, scalar, the gluon currents, so the either the GG or GG tilde. And then there's another diagram possible where your dark matter couples to a pion, and then the pion attaches to the nucleon. Right? It's still scattering on one nucleon, but it's through a pion exchange. And this will happen for, let's say, a pseudoscalar, while the axial current, both of these would be of leading order in our counting. Right? So that's the leading order contribution. So now if we collect everything, we have an answer of how you go from the coupling of dark matter to quarks, gluons, and photons to these non-relativistic operators. So we used chiral effective theory, and we have a translation. So this would be the coefficient. So the resolution is not great, but this would be the coefficient which sits in front of these operators, and then there's a Wilson coefficient from this side, and then there's a bunch of form factors that you can't even see. But that's it. No? So like you do this formalism, that's what we accomplished. Now is we translated from this theory to that theory using chiral effective theory. Right. Okay. So now comes a series of sort of visual results of what have we learned. No? So first statement was this one. So what's often done in a global analysis, or what's used to be done, is the following. So you take one non-relativistic operator and keep coefficients Q independent. So for instance, let's say I just took a random paper, not to blame them too much, from Z0 to 100. So you take one operator and you put a bound on the coefficient in front. So in this case it will be perfectly valid, but maybe for all three that's not a good assumption. And we want to understand why this is not good. So I'll show you why this is not good. And the reason why we don't want to do this really, so it's because even if you have heavy mediators that are integrated out, so they're much heavier than the QCD scale, you still have a Q dependence which is coming from the pion poles and from the exchange of the photons. Right? However, we do know how this Q dependence looks like, so we can just take it into account. All right, so first the pion post. So they enter in many of these, in the matching of many of these relativistic operators. For instance, if I take the axial times axial current, this will you'll have a contribution which is a pion pole, which multiplies this operator. So this operator, I read it off now. So it's the spin of dark matter times the momentum exchange, and spin of the nucleon times the momentum exchange. And then there are many. So it's coupling to GG tilde with the pseudoscalar coupling. All of them have a Q square dependence. There's also a set of operators that will contribute to, for instance, the number operator for dark matter, and then spin of the nucleon times the momentum exchange. And again, there's a bunch of operators we get the pion poles. All right. All right. So why is this? What does this mean? No? So it means the following. So let's say if I take the classical axial operator, so I have an axial current on the dark matter side, axial current on the quark side. So this will match onto two non-relativistic operators. So one is the spin times spin, where there's no pion pole. This is just the axial charge of a proton for a particular quark, for instance. And however, there's another contribution, which in our counting is of the same size. We'll see in a minute what does this mean. Which does have a pole. Right? So there's a 1 over Q squared here, and there's a Q times Q upstairs, so you see that parametrically they look the same. Okay, so numerically, however, so what I'm plotting here is I'm just picking a particular choice for the Wilson coefficient. So let's say that you couple with opposite but equal size to up quarks and down quarks. The coupling is to the axial operator and the axial current for the dark matter. And what's shown here are, schematically it would be the bound that you would get with some exposure, in this case in a xenon experiment. These are arbitrary units, they will change depending on what the exposure is. If you do the following, you have a prediction where you only keep the spin times spin operator, so that's this dashed line, or you also include this Q squared suppressed by 1 over m pi squared plus Q squared enhanced contribution. And you see that on the log scale, the difference is not big. Actually, when I said order 1, numerically this means more like 20% unless you cancel the two contributions. So what's plotted here is, instead of fixing this ratio, you take the coupling to up quarks to be 1, and then you vary the coupling to d quarks, and you see that it's never really big, this correction. Sort of, order 1 in this case really meant 20% correction. So you could say, whatever people were doing, it's fine, it's only a 20% correction. I mean, what people were doing is they were just keeping this operator. However, order 1 can also mean 7, So order 1, so you see this order 1 really means order a few, So in previous case it was a factor of a 5 smaller, the other contribution. Now we'll see that it can also be a factor of a few bigger. So let me pick a different operator. Let's say a scalar operator on dark matter side, and then a GG tilde on the standard model side, and then let's do the same thing. So I forget about the poles. This would be this dash line, so that's the exclusion. Or I keep also this contribution that comes from the pion exchange, which we said that it should be of the same order. And it changes by really a factor of 7 depending on the dark matter mass. So if dark matter mass is light, then it's a small effect. If it's big, then it's a big effect. Alright. Let me show you one more. So I'll take yet another operator, but show you a different thing. So for instance, if I take now a pseudoscalar coupling times GG tilde, and you scatter on fluorine or on xenon. So the dashed line here means no Q-square dependence in the poles, so you forget about the poles. The full line means you do include the poles, and you see that the effect on fluorine is very small, but the effect on, let's say, xenon 131, it's a huge effect. So it means that if you don't include these order 1 corrections, no parametrically order 1, you could completely misinterpret what you're seeing. So for instance, if you have a signal in fluorine, but nothing in xenon, in one case you might think that you're fine if you have a full Q-square dependence, but if you forget about the poles, you would say that you're even excluding this model, maybe. All right? I have in the backup slides. I have more examples, so it's not just. Oh, it's a question. First question. That's awesome. That's awesome. It's a question, no?
It's a question.
Yeah, yes, keep going.
No, I was just wondering. It's supposed to be a special role in gluons because those are the ones featured more.
Oh, no, so I have another one with just a pseudoscalar coupling in the backup slides. I just picked something.
Yeah, but...
so it's really, okay, so it's really...
So what is the reason why in the first case you don't have a huge...
Oh, it's just numerical prefactors that I'm not showing.
Okay.
Yeah. I mean, it's just like...
I thought there was something with the gluon that
so there is... But for the pseudoscalar, it's actually a bigger effect. So I would like to say that it's the pion mass, which is bigger than the typical 60 MeV. So that's the explanation for the axial current, because the couplings are really related.
Okay.
But for the pseudoscalar, actually, the factor is not just one, so it is a slightly bigger effect. Here, it's you saw that it's not the pion mass that really matters.
So, I mean, I also have a question.
Yes.
So, okay, I read the question first. So, I mean, even if you include the pion pole, I mean, wouldn't you say that you have an uncertainty which is still big?
There are many uncertainties.
I mean, wouldn't you just want to compute these matrix elements non-perturbatively on the lattice? And that's
absolutely. This would be a dream. This would be fantastic. But the problem is that xenon, it's, yes.
This is
so
very
it's 131 and it's...
nuclei, I mean, at least on nucleon.
No, so okay, maybe I don't quite understand what you're asking, but in order to stick this into a nuclear physics program, no,
so
you need to tell me how it couples to nucleon and protons, and you need to tell me how, whether it's a single current or coupling to two nucleons at the same time. And I think the only real tool that we have, it's not perfect, is this chiral EFT. There are still quite a few bones buried underneath. So I would say, okay, so I think where we are, so let's say where we are now. We are, I think, at the stage where we can comfortably say that maybe we have cross sections up to a factor of a few. Some of them are quite precise, not the spin independent. Spin dependent also it looks pretty good, no? But for this type of operators, I'm not
so
sure.
how many? I mean, so this would involve, let's say, single nucleon and two nucleon matrix elements. Is that correct?
Yeah. So this one not. So I actually will not show you anything about the two nucleon matrix elements. I will just move on. The only thing I said was that they can be a sort of 20 to 30% correction, which is roughly what you see. There's not too many people calculated them. No, it's the Hofer-Richter group have the calculation, and it's a particular calculation. So I mean, it would be ideal that there would be many different nuclear physics methods used, so you know what's going on. Because there are approximations when they do this. No, it's a mean field approximation when they do this, and that actually potentially enhances the two nucleon contributions. That's it.
This slide is you looking at xenon the element, whereas the previous one was you looking at the modifications from the actual experimental.
Oh yeah, so I just show you the, so this is the, in terms of the momentum.
Yeah.
Yeah.
But the previous slide was the correction, the modifications to the limits, or?
Yeah, exactly. So this is now like you take this distribution,
Yeah.
you assume something for the threshold,
Yeah.
and then I just assume there's an exposure and some lambda, which is pretty crazy here, not 25 GeV, but still valid. No? It's a valid DFT. Whether it would survive the limits from all the other experiments is a different story.
Okay.
Oops. Anything else?
No.
All right. All right. So then there was the other type of 1 over q squareds was coming from the photon pole. So this was the first operator that I showed. Also the magnetic moment of dark matter. And we said this populates 4 non-relativistic operators. Some of them don't have a pole, and the other ones do have this photon pole. No? And then there's the electric dipole, also has a 1 over q squared pole, but there is also a q dependence here, so effectively just 1 over q. So let's see what this means. So basically, I already gave you the information on this slide yesterday. I'm just adding a picture. So what's going on is we take the magnetic dipole interaction, and then we do the non-perturbative matching. So the non-perturbative matching in this case is simple. It's just an exchange of a photon. And we have either, you see a charge of the proton, or you see the magnetic moment of the neutron or proton, and this gives you these 3 other operators. And depending on what the dark matter mass is, you see that some of them scale as 1 over dark matter mass, the other guys scale with the nucleon, so the 1 GeV neutron proton. What's plotted here is the contributions to the cross section converted into the effective limit from different operators. So let's say if I just switch this one on, but take all the other coefficients just to be 0, no? Just brute force, you'll get the blue line, and then the yellow line would come from this guy down there, and then the red lines are contributions from these 2 operators. So the higher up you are, the smaller the contribution in this case. This is for scattering on xenon, right? So for xenon, let's say the blue and the yellow lines are important. And now let me switch to fluorine, and the only thing you want to see is that the color is completely changed. So the blue and the yellow line are irrelevant, and then the red and the green are important. So in other words, there are 2 degrees of freedom here. So it's the dark matter mass and the choice of the scatterer, so the nucleus that you scatter on, and this can completely reshuffle the importance of different operators. So you need to keep all of them if you want to properly describe the magnetic moment. So if you have a dark matter with a magnetic moment. All right. So what are the take-home messages? So UV physics will often populate several non-relativistic operators. So this crucial thing here is often, so I'll try to quantify what this often means in a second. So for us to do that, I'll have to connect to the high scales. No? So this statement requires an assumption about the UV scale physics. All right, so what we'll do now is, so far we worked at this low energy, so we wrote the effective theories, let's say at scale of 2 GeV. Now we want to relate to a high scale. So UV theory, which for us will assume that it sits well above the electroweak scale, and then we'll do these different steps. So first we'll integrate out the mediators, means I'll just show you what the resulting basis is of the operators. And then we'll go the running in the full standard model, then integrate out the WZ Higgs on the top when you reach the Z mass, so the electroweak scale, and then the QCD and QED running. So don't worry, it will be just pictures. No? So we're almost done with formulas. So the only formulas will be just the operators. I want to show at least the operator base, especially because there were questions yesterday, even without Candy, so I'm very happy. Alright, so what are we doing now? There's one assumption is where the dark matter mass is. So we'll assume that the dark matter mass is at the electroweak scale. Right now, and later I promised you that I will change this assumption also. And then we allow for dark matter to have electroweak charges. So it's really probably that's the most complete EFT that you can think of. And then we have the EFT Lagrangian. So it means that I have the renormalizable interactions of dark matter with W and Z, and on top of it we plug in also the extra higher dimensional operators, and they're grouped according to dimensions. There will be dimension 5, dimension 6, dimension 7. And then the status is that this is known, the basis is known. The RG running is only computed for dimension 5, dimension 6 for Dirac fermion dark matter so far. Alright, so we're up here and we'll look at the basis. So we allow for electroweak charges of dark matter, and here I assume Dirac dark matter, and there's it's only 8 operators, and they have so these guys have a structure that you know already, so it's the equivalent of the magnetic moment, but now with a hypercharge, or you can also couple to the W, the triplets of the W's, because the chi I said carries the electroweak charges. So they're in some multiplet, and this is the generator of SU2 in that particular representation. And then there's the currents where you couple to the Higgs. This operator we also saw. This was the operator, the dimension 5 operator we generated in the toy model yesterday. Then there's the version where you just plug in a gamma 5. So this is CP even and a CP odd set of operators. Now if you go to dimension 6, still fits on one slide. I won't read all of them, but the structure is either coupled to core currents, so these are now really like a vector currents, or the lepton currents, or the Higgs current, where in this case you have a derivative acting on the right and the left. And that's the full set of dimension 6 operators. And then if I go to dimension 7, I don't show all of them, because you see the scary numbers on the left. So it's 22 gauge operators, 12 gauge Higgs operators. You have a form like this. You have coupled to hypercharge the Higgs. 6 4 Higgs operators, 10 2 Higgs. I mean, I'm getting tired even reading, no? How many there are? 18 Mikava-like operators, 14 4 fermion operators. Alright, so you see that, so first of all, you learn there's quite a few. This, I don't even count the Flair multiplicities. So these numbers you have to compare with 22 that we had at the low energy. Alright, so didn't get the question, but I will answer nevertheless this question. So am I completely crazy if I'm considering these higher dimensional operators? Because I do have renormalizable electroweak interactions. So usually the renormalizable interaction will give me the leading contribution. It's dimension 4, so it's less than dimension 5, it's less than dimension 6. The reason is experimental, phenomenological. We know that if I have just a 3-level Z exchange, this was excluded in the dark edges of dark matter detection. So as soon as you switched on the detectors, it was excluded. Alright, so what does this mean? It means that the theories... one second, sorry. If you have a 3-level Z exchange, it's ruled out by direct detection, so without any suppression. So don't talk about the Majorana. So it's just the Dirac fermion with the coupling to the Z, which is what I'm doing right now. If if you have the neutral guy coupling to the Z, that's it. No, that theory is dead. So the only options are where you don't have a coupling to the Z. So it's a particular.
How do you forbid that?
Oh, you just take a hypercharge charge to 0, and then it's a, you have to have, so the triplet needs to be, so let's say if it's a triplet, it will be the middle guy, not so. So there's just a subset of representations that will have a no coupling to the Z. Alright, so what this means is that the theories that will work would have contributions that come from renormalizable interactions that will start at one loop, but they're through a Higgs exchange, so there's a penalty here. So effectively they will be of two-loop order, and that is highly suppressed. So let me, highly suppressed, let me, oh, very good. Awesome. Yes.
If you're giving dark matter a certain representation now, for instance, in that example you make in SU2 triplet with hypercharged Jure, shouldn't you also have operators with a single chi field?
No, so here there's, so either you assume a Z2, here I assume that there is a global U1, so that's why there was chi bar.
Sure.
Yeah. Okay. So, yeah, but that's part of the building the EFT. I have to assume what the dark matter symmetry properties are.
Do you know if people are interested in something single chi fields, or is it?
Oh, the decaying dark matter?
Yeah.
Yeah. So that would be another. Yeah. So, yeah. Okay. So it's a very unexplored field in terms of the EFT. So if you try to build the EFT, so the decaying dark matter, usually you put just bounds on chi, just couples to something which is BB bar and so on.
Sure.
You could try to do this much more systematically if you want, but it was not done. Nobody really did it.
Okay.
All right. Sorry. Anything more? All right. So I scared you enough, I guess, with this throw. Okay. All right. So that's the reason. No? So when I show this pictorially, so what I show is, let me do the following. So let's say I switch on these higher dimensional operators, and I ask, I switch one at a time, and I ask what need the suppression be in order to compete with the standard model contributions. So these renormalizable contributions. So these are there, and let's say I take electroweak triplet dark matter. It's hard to read, so let's say this blue line here is, I have a pseudoscalar current times h dagger h, and what's plotted here is the scale in TeVs that suppresses this operator. So if the scale is above this line, it means the contribution from this higher dimensional operator will be smaller than these two-loop contributions. If you're below, then it will be bigger. So let's say if I have, what does this mean? So if I have a coupling, so if I have a theory where the mediator has a mass of 10 TeV, I'm below the line, no? So that means that it will dominate over this effect. So maybe I should look at this chi bar chi h dagger h, because that's the one where I showed you the toy model. So if the mass of the mediator is below 10 TeV, this would be this down here, it's way below this line. For our toy model, with the mediator of 10 TeV, so well above the electroweak scale, with all the couplings order 1, exactly 1, no? So that was our toy model, you would dominate over these two-loop contributions. No? So quite a heavy mediator. And it depends on the structure. For instance, if you switch on the electric dipole, which is this green line, it means that even a mediator as heavy as 10 to the 4 will dominate over these two-loop contributions in direct detection. So it all depends now on the details, whether or not you're supposed to keep the higher dimensional operators. So let me also go over this side. So this was dimension 5 operators. This one is dimension 6, a few examples. So for instance, in this yellow line, it's hard to read, but it's quite important, unfortunately. We'll use it. So it's a vector current times the axial current to up and down quarks. So this is highly suppressed, so only the mediators of a mass which is below 100 GeV would dominate. No? So these guys would always dominate for any reasonable theory. However, if I have a vector times vector coupling, we are at, let's say if you have a 50 TeV mediator, this would dominate over these two loop contributions. So it's quite striking. So the only difference between the blue and the yellow line is this is a vector current on the quark side, and this is the axial current on the quark side. Yes.
So can you give a concrete example of a model that has dimension 7 operators but not dimension 5 and 6?
Can I come up with? So why are you asking me about dimension 7?
Why do
It's
you
a
care
jump.
about dimension 7? I mean, that's
Oh, I didn't mention dimension 7. So dimension 7 would be harder. So that's why the only thing we did was write an EFT basis, and that's it. No, I don't know how much time you want to spend on that. I don't know. So I didn't really think through how many of the UV completions would match onto dimension 7. I don't know.
And how about dimension 6?
So
versus
some of the,
5?
okay, so let me be more concrete. So some of the dimension 7, it's easy because I just switched over the Yukawas there. So this should be relatively easy to write down some scalar. But many of the other ones are probably going to be very hard to. I will spend, actually, where I will spend time on is show you the what's going on in the mixing for dimension 5 and dimension 6, and I'll also give you maybe a bit of, it will be quite easy to see, let's say, a very simple model for the generators dimension 6. I will not show it, but I can say more. Okay, anything else? Yes.
No, I have it. No, I don't want to candy. I was just wondering, I suppose that it would be easier for the standard model contribution to dominate if you now increase the representation of the dark matter. So if now you go to quintuplet dark matter, the standard model contribution would be higher.
Yeah, okay, it's not so simple because there's cancellations going on, but generally you're right, yes.
Okay.
Yeah.
I'm thinking about minimal dark matter, but
Yes,
I know
minimal
it's
dark
not
matter.
this scenario.
That's very good. Yeah, so minimal dark matter is another example where it would be nice to see like systematically what goes on.
Which is not done
Because
so
it
far.
was not done, yeah, exactly.
Yeah,
That's actually a very interesting. We have many papers to write.
So what is
But it's true.
minimal
It's
dark
because you see, like, you already know what we're going on. Because if you do something to the the minimal dark matter, no? You know what you want to do in order to increase the cross section is you want to generate this guy, no?
Yeah.
And you want to violate CP, and only thing you know about this is just the low, the representation. So maybe so that everybody can follow. So minimal dark matter idea is that you want to know why dark matter is stable, and you just look at the representation, and there's two models that survive, and one is the preferred one just because it has only one coupling, you know? And that's called the minimal dark matter, and it's a quintuplet.
It's a quintuplet.
It's a quintuplet.
If it is a fermion, it's a quintuplet.
Yeah, exactly.
If it is
It's
a
a fermion.
scalar, I think it's a septuplet.
Yes.
A septuplet.
Yeah, exactly. And that one is yellow coded because there's two other couplings, so you don't really know what the cross section is. So you're right that it would be. I think it would be quite nice to know how easy it would be to write I think it would be very easy, to write down a complete model where you would have an enhanced direct detection cross section, And that would be important because, let's say that you discover minimal dark matter, and you want to know whether it's a minimal dark matter, you will want to know the annihilation cross-section and the scattering cross-section. Exactly. And then you will see that you will be sensitive to UV physics, in the same way as you are for the scalar version. So both of them will be yellow. I think that's my conjecture. But you're right on the money. So I think it's a very good project. Anything else? Oh, we went in the diagonal direction right now. Okay, so let's come back. So what I'll do next is ask a few questions. So now we are equipped to ask the following. How often do you generate just one operator? And another question is that I asked yesterday is what's the reason why we were able to stop at second order in derivatives on this non-relativistic basis. Now we have the counting, and this counting will give us the leading contributions, and we can see what, systematically see which operators in it. So for instance, if I take general dimension 5 and 6 EFT above the electro weak, at leading order you require only these encircled operators out of the 15. Now if I enlarge this to dimension 7, there's only one extra that you generate, so there's 5 of them that you don't generate, so you could just forget about them. The reason why you need to go to a second order in the derivatives is also clear, because I have this 1 over q squared pose. So you don't have to go to q cubed, but you do need to keep a subset of q squared operators. Now let's ask a different question. So the inverse problem. So let's say which of these operators, non-relativistic operators, can I find a UV model that will only generate that operator? So if I switch on one operator in the UV, and I will just end up with one operator in the deep IR. Alright, so if I assume 5 and dimension 5 and 6, there are only 2 in this counting. So it's this spin independent one, and then surprisingly this O11, I would have never guessed. But not the others. So all these other guys, for instance, spin times spin, in our counting, this would be accompanied by O6. We said it was only a 20% correction, but this is order 1. No? It's order 1, but there are still some uncertainties when I say order 1. Alright, if I assume dimension 7, sorry.
Yes. Sorry, the blue ones, the ones you signal as the blue are the ones that can appear by themselves.
Yes, oh, absolutely, it was not clear, yeah. So, this guy, there's an operator. There's actually 2 sets of operators. It's a vector times vector will give me this guy, or a scalar times scalar will give me the spin independent scattering. So there's quite a few UV operators that will just give me this operator. For the rest, you will populate different, so it will match onto several non-relativistic operators. So you see, so I mean, what I'm saying is that it will be very hard to cook up a UV, like a physics model where you're switching on, for instance, just O3 in the IR. It's like, as soon as I'm integrating out the mediators, I cannot do it. So you have to change physics at the 2 GeV. So I'll show this. So there will be 4. So again, so the message was okay. So the message is it's really tough to interpret. Oh, very good.
I've already got one. It's okay. Do you have mixing between these operators?
Yes, that's the next topic.
Okay. Well, can I just ask, when you say you can switch on one by one, is that neglecting mixing, or is that saying even with mixing this individual one?
Oh, right now no mixing. Yes.
Okay.
So there was no mixing, but so now I ended with this story, and now I'll switch over. I think the way to okay, so this is, I would say, more for historical reasons. Now it's just I want to drive home the message that it will be really tough to build models where you scan over the non-relativistic coefficients in the IR. What's I think more interesting is just the technique. No? So I have my UV model, so some dark matter model, and I want to know what the prediction is for cross-section, and I will show you what the ingredients are. So we'll go over the steps, and there will be mixing and all this stuff. So you don't want to share candy around?
I'll share.
Alright, yes. Alright, so what I do now is I relate these different scales. So we want to start at the UV and then we'll go down to the these non-relativistic nucleons. So first I'll show two examples how this works at 3 level without mixing, and then we'll show that the loops can be important. Alright, so our celebrated magnetic dipole. So the magnetic dipole above the electroweak looks now like 2 operators. So it's either coupled to the hypercharge or you couple to the W. And then what happens at the electroweak scale is very easy. You just project out the direction of B and W3, that is the photon. So the Z gets thrown out, so it's integrated out, so I only keep the photon. So it's one combination survives. And then you go down and then you populate this set of 4 operators. So in terms of the cross-section now, even though I switched on just 2 operators, it looks pretty horrible. No, I have a very complicated expression. The scalings are either with 1 over m chi squared, but it's enhanced by coherent scattering, or there's these pieces which are 1 over m squared. So that's why it was so complicated, what the mass of the dark matter was, what the nucleus was, and so on. No? So this electroweak stuff was easy, but then it gets very hairy down there. Another example that I show, which will be quite important for us, is I just take a set of these vector operators. So either you couple to the left-handed or the right-handed currents. So this is, so the model maybe you want to have in mind is some Z prime model. No? So for instance, you would mix with the vector as a question. No? Think you ask, what's here you ask. So so you would have mixing with the vector like fermions. This would be gauged, and you also it's the same Z prime also couples to dark matter. So that would be the model in words. Alright, so electroweak matching is very simple. You just forget about the top quarks. And then if you look at the low energy, then it depends what the charges were of the Z prime. No? So if I have just some random charges, I will end up with the leading coefficient, leading operator will be vector times vector. No? So I just pick a vector part of the left-handed, a vector part of the right-handed guys. No? And this will give me coherent scattering. Right? So it would be this Wm function, it's A squared enhanced, it's a coherent scattering. Now it's a very different story if you have a very particular model, which is that you couple with the opposite signs to left-handed and right-handed guys. Now, so maybe if there are model builders among you, it's not so crazy, for instance. Why? Because these are really different standard model groups, and it would be like this would be exactly the assignments that you would end up, for instance, in Froggatt-Nielsen models that are gauged. Because the left-handed and the right-handed guys have exactly the opposite charges, up to they could have exactly opposite charges, I should say. Alright, so you could imagine easily that if you have couple to left and the right with the opposite charges, it means that you're cancelling this piece, no? Right, so the left and the right are opposite, so it means that the vector piece cancels, and I end up with the axial. Vector times axial is heavily suppressed. That was the yellow line in the slides before. So it's suppressed either by the velocity of the dark matter or the momentum exchange, couples to the spin. So this gives you a highly suppressed. Now there's this v squared, q squared, or m chi squared, m should be mn squared suppression, right? All right. So, but in order for this to be true, you need a cancellation which is very precise at the 10 to the minus 6 level in the electroweak. And this is something that will change when you run. So one loop correction will change. And that's why it will be important to include corrections. All right, so I'll go now over the steps, and I will show also the example what happens to these axial operators. All right, so we'll start. So we've done the first step. Now we'll do the electroweak running. The electroweak running so there's mixing of dimension 5 operators. So for instance, what happens here is I have a mixing between the magnetic moments with B and the W. And this would mean that, for instance, if you were to fine-tune your theory such that you only have a Z coupling to the Z through this higher dimensional operator, at one loop you will generate also coupling to the photon, so you can't fine-tune. Right? So you can't get rid of this magnetic dipose. For dimension 6, it will be the exchanges like this, and there are two types. So it's either, so these are present only if you have dark matter which has electroweak charges. And note that the left-handed and right-handed guys will run differently. No? So there's no line like this with the W if I have a right-handed guy here. No? And then there's also mixing where even if dark matter is a singlet, they will be there, just showing one, there's others. So let's say you have a quark loop and you meet a B field. Alright, so what does this mean for our example? So I said we had this highly suppressed vector times axial operator. And we fine-tuned the theory such that you said in the UV I will only generate this guy. Now I had the opposite charges to left and the right. But at one loop you will jump to this prediction which corresponds to the blue line. So in terms of the limits, so the limit that you would deduce on this operator, vector times axial, if you don't include the running, would be here. If you include the running, so this is log scale. So you're off by 2 orders of magnitude in your interpretation. Okay. All right. So, so we've done the mixing. So next step is integrating out W, Z, and the Higgs. I also show this pictorially. For instance, if you have an operator like this, you integrate out the Z, and you end up, for instance, with the 4 Fermi operators. Even though you start with a Higgs current, if you have a Higgs exchange, for instance, this guy will lead to a scalar times scalar operator. So what you're doing is just you're integrating degrees of freedom out, and you're ending up with local operators. The next step now is running below the electroweak. So this is very simple because you only run the currents. No? So there's nothing to do on the dark matter side. Dark matter side is inert, doesn't have color charges. So this is well known, I don't know, from 70s, I guess, 80s. There's one, phonologically it's interesting still, because you mix leptons and quarks. So for instance, if I have dark matter that you say only couples to quark, at one loop you will generate a leptophilic dark matter. So at one loop you will have a coupling to electrons. And then at the quark flavor, so at top, bottom charm, you integrate the quarks and you generate the couplings to gluons. Since proton and neutrons have a lot of gluon content, this will be a big piece of the direct detection cross-section. Alright, there's one wrinkle here. Surprisingly, you also need to include the electroweak corrections below the electroweak scale. It's very counterintuitive. This is to have order 1 for every imaginable operator. So how this works is, you include two insertions of these electroweak exchanges. So this would be the dark matter coupling, the effective one, and this is just the standard model, let's say a Z exchange. The reason why I need to do it is because for the B and C quarks, this may be a leading contribution coming from the running below. All right.
Yeah, Jure, can
Yes.
you go back to that diagram?
Yeah.
Is it quadratically divergent?
Okay. So there is it's quite an interesting story of how you interpret this. There's log divergences here that have to do with what you do at the matching scale at the electroweak. And we can talk more afterwards because I don't know how much we can learn by just showing. I want to show you more, but I thought just to mention it so that you know what's under the hood, right? And we can talk more. I mean, I think I need like 10 minutes to explain properly what's going on. Unfortunately, there are slides in the backup slides. I threw them out. This morning at 2 a.m. I decided I can't do it. But I'm happy to talk offline. It really takes just time. But it's quite an interesting story, I think. Sorry. And the candy, yes. Yes. All right, so let me recap. No, there's a lot of moving parts. So what did we accomplish was so the good news is dark matter UV theory. Any dark matter UV theory above the electroweak we have a systematic way to obtain the leading order prediction for cross section. You will need to integrate other mediators by hand, and then it matches onto this tower of EFT. So this running and matching down to the nuclear scales. So that's the good news. There is the framework. However, not all the pieces are there yet. If you have a Dirac fermion, it's there. However, if you have a scalar dark matter or several multiplets, it's still there are missing pieces. But it will be filled out. No? So, all right. So the very good news, I should say, no, is that all of the above, so my first lecture and today's lecture, is available in a program DirectDM. It's a Python or a Mathematica package. So it performs the IG running and the matchings, matches onto this non-artistic EFT, and then calls another package, I should have cited Hexton and company, for the nuclear response functions. Alright, so the thing is, so you can basically forget about this lecture. No? The only thing that you need to remember is this slide, and you have a feel for what's under the hood. No? Right, so there's the running, and the promise is leading order cross section. So what the precision is, it depends on the details, but at least the leading order should be there. Right? Okay. So now I'm switching gears completely. And I'll talk about the heavy dark matter with only renormalizable electroweak interactions. So I'll do the following. So I'll take the limit where dark matter will be heavy, much heavier than the electroweak scale. And then I'll do two problems. So dark matter scattering in direct detection, and then dark matter annihilation to photons. And we'll do this for the WINO. So the WINO, for people that, so this used to be that if you said WINO, everybody knew exactly what you mean, or actually if you talked about the non-MSSM model, you should always translate back into MSSM. I think now we're in an era where if I say WINO, I need to say what the hell this is. So it's an electroweak triplet, and we'll use this as an example. Alright, so the first thing I'll do, so now there will be some equations, but I'll give you the physics of what's going on. So we'll need to match onto the heavy dark matter effective theory. So dark matter is non-relativistic for energies below the dark matter mass. And you want to build a theory where you integrate out the mass. So that's a concept which sounds quite weird, but what you really want to do is there's a part of the kinematics which is super boring. Now I have a heavy object, so I'll use this. No? So this is my rock, so this is the second prop I'm using. It's heavy, and what it does, it just sits here. And let's say that it sources a field, so let's say it sources the electroweak W's and Z's, so this thing is now surrounded. Alright, so it's surrounded by the W's and Z's, it's a cloud of W's and Z's, right? And then what I want to describe is the interactions with this dark matter surrounded in the cloud when it's moving. No? So, alright, so it's moving and you see that this is fluttering around, but most of the kinematics comes not from the bag, but from the heavy object inside. Alright? And it's a completely boring thing, no? So I want to know how this thing is behaving. I don't care about this Newtonian thing where it's, it's the trajectory. So I don't care about the trajectory. That's the trivial stuff. So how do I deal with this, no? Well, I take it out, no, out of the equations. The way you do it in quantum mechanics. So what does it do, no? So if I have a mass or an energy, so what does it do? It will just give me a phase, no? So I have an energy times, so this would be the momentum times x. Now it gives me a phase. So when I evolve the state, it just gives me the phase shift, right? And this is a trivial phase shift. For instance, this is a 4 velocity. If it's at rest in the left frame, no, this 4 velocity is just 1 for the 0 component and 0 for the 3 momentum. So it's just picks up the mass, no? And it has a phase which will be e to the im times time. So it's just a time evolution of a guy that is very boring, it sits here. So you want to take this out, and then, so that means I multiply so I take this out and I define two fields, the small chi v and a capital chi v. So I can also write it in a different way. So I start with my dark matter field and I multiply with 1 plus v slash. So v slash is this v here times the gamma mu. This will project out the large component. So basically it projects out the particle out of here. And then there's a small component from the spinor. No? So this would be the antiparticle when you have 1 minus v slash. Right? So there are two things going on. There's the physics, so what's behind, why we're doing this, and then there's the technicalities. No? So it's what you really define as a chi v is exactly this. No? All right. Okay. All right. So now we have the following. So what's going on now is there's one more thing we need to do. We need to integrate out these antiparticles. So these antiparticles, you see, has the same phase, where if it's an antiparticle, it's exactly the opposite phase that it will have. You have to have e to the minus the mass. No? There's this notion that the particle propagates forward in time, antiparticle backward in time. No, that just has to do with the phase that sits in front of the Did I completely lose you? Oh wow, okay. Not even candy can help, I see. So we'll be done quickly with this. So there's just a few things I want to highlight. No? So I'm integrating out the heavy modes, and it's something super weird now. I'm taking a field, no? And I'm integrating out only part of the modes connected with this field. No? So the field has the particle and the antiparticle modes, and I'm integrating out the antiparticle guys, because if I want to convert my particle into antiparticle, I have to bring in twice the mass. No? So I have to have a big kick in order to convert this guy to some antiparticle. No? I have to create a particle-antiparticle pair. Right? So it will be a huge momentum kick, and this will not happen in my theory, where the only thing I have is a guy sitting and a W fluffing around. Right? So I will take it out, yes.
Can you use this approach? It's not a good question, don't worry. Can you
Yeah,
use
it's
this approach
fine.
if you have a very small Yukawa coupling, Or is it still valid in the lighter regime but a small Yukawa coupling for this reason or not?
Yeah, so this has actually nothing to do with the interactions.
Yeah.
So you can have a dark matter which doesn't even interact with the renormalizable interactions. You still want to do this, and it will be clear why. I'll say in a few slides. I think you can share the. So good question actually. Anything else? Oh, awesome.
Does this effectively map onto like an asymmetric dark matter EFT?
No. I mean, you could, but it really doesn't have to do anything with the whether it's asymmetric or not. Just that it's heavy, much heavier than the interactions. I mean, should say it's heavier than the energy at which you will do the process.
Right, but that, like, I mean, right here it feels like you effectively just have one of the modes participating in the interaction because that's all you kind of kinematically
No, I don't want to give this impression. So if you have a particle, antiparticle annihilation, you want to do the same thing for the antiparticle leg, but with the sign switch. So you will have two, this will be a bit more complicated, you will have two EFTs, one describes the particle, the other one antiparticle, and then they combine. Anything else? Alright, so we're almost there. So the next step is you integrate this guy out, and I end up with a Lagrangian which looks something like this. Alright, so let me motivate. So v dot the derivative. So this will give me the time derivative. So it will just be the time derivative. The time derivative is the energy. And then I end up with a perp component. So I subtract the 0, and I only have the 3 momenta. No? So this would be the kinetic energy. No? This is the, you see this? That this is just, you subtract away in this formalism the 0 component here. No? Alright, so I have the kinetic energy, which looks like a relativistic kinetic energy, and this will give me the energy. Right? So you see that this is a non-relativistic Lagrangian. So it's a non-relativistic field. It also would be called non-relativistic dark matter. And all this comes from heavy quark effective theory, or the NRQCD. So it just borrows the formalism from the QCD and QED people and applies it to the heavy dark matter. Alright. Okay, so now we're ready to understand what will happen next. So I said, so it looks very similar, the slide, from what I had before, but the tower is different. So there were two changes. So instead of a lambda here, there's a dark matter mass. So our UV theory is a we know plus the standard model. And then the first threshold is not the mediator, but will be we want to integrate out the mass, but not the particle. So we'll end up with a heavy dark matter effective theory, which has couplings to W and the Z. And then all the rest of this box is the same as before, right? So you don't have to do anything, right? So secretly, now you also see that what I did not show you is that before we also did exactly this. We matched onto the heavy dark matter EFTs at this stage, but I didn't show you the details. No? So in the code, under the hood, that's what goes on. But it's super trivial in that case. It doesn't buy you anything. No? Okay. All right. So at this stage, we integrate out the dark matter mass, but not the particle. And the Lagrangian looks like this. So I'm just keeping the contributions which are not suppressed with dark matter mass. Now this HV is a triplet of states. So we know has 3 components: the positive charged, the neutral, and the negatively charged component. There's couplings to W's because it's a triplet. And then there's the time derivative. So there are 2 surprising things here. So there's no gamma mu's. No? So the spin is completely irrelevant here. So it doesn't matter how you orient the spin. No? It doesn't matter how you orient the spin. it completely disappeared from the theory, and the mass also completely disappeared from the theory. Right? So it was completely inert. So the reason why it doesn't appear is because you come in with the heavy mass in, and then you also take exactly the same heavy mass out. So it doesn't matter how heavy it is, it's just the relative kick that you give, which has little to do with dark matter mass, has more to do with how heavy the nucleus is. No? So imagine, so now dark matter is the track, it's huge, no? It will be 3 TeV. The nucleus is a ping pong ball, it's 100 GeV. All right, I'm exaggerating a little bit, no? So it's really, the proper way of thinking about this is the dark matter is at rest, and then you throw the nucleus at it, and it recoils, and the dark matter mass doesn't budge. No? It's really what's going on with the nucleus that matters. No? All right. And you see, at some point it doesn't matter, no? Whether you throw a ping pong ball at a brick or a truck, it doesn't matter, no? It will always it will always give the same momentum kick. No? So the mass completely disappears, and formally you can see this in the Lagrangian itself. There's no mass. All right. There were two interesting things here. All right. So from here on, it's sort of the stuff that we know, but we didn't really do it. No? So I show you. So now what's going on is that this solid line, so the double solid line means the heavy dark matter, and then you need to match the electroweak scale, means you need to integrate out the Higgs or a W, and you will end up with the point interactions of dark matter with quarks, and then you'll also do this. You have to do this at 2 loops. The reason is that because at 2 loops you will generate couplings to gluons. Proton and neutron have a big gluon content, so just numerically this will be a big effect. And this, the way you do the matching is you have an operator with a gluon, but you need to subtract the pieces where in the EFT below the electroweak you integrate up. You also give the contribution at 1 loop from the quarks running in the loop. All right. So that's the matching. So you perform the matching and you end up with these coefficients. And then you run down. And the way this theory looks like, so I'm showing this for a reason. Because so some of the operators you recognize, so all of them have a chi-v bar in front. So it's just a scalar operator. However, there are pieces that are, for instance, this would be mq bar q, which is the operator we've seen, but there are also pieces which go as the velocity v mu v nu, and these are not suppressed. All right, I've not shown you these operators yet, but they are sitting there because the time components of the operators are different than the 3 components of the operators, because we are in the non-relativistic limit. That's one way of thinking about this. Is these v mu's have no penalty, so you just count the dimensions, and you will see that you have a larger set of operators if you have a heavy non-relativistic dark matter than if you have a non-relativistic. If you have a relativistic dark matter, you have a smaller set than if you have a non-relativistic dark matter. All right? If this was a relativistic dark matter, this would be replaced with the momentum of dark matter, which would be small. No? You would pay a mass of dark matter. All right, and these are the operators. Okay, maybe I showed too many details, but I thought it was important to at least have this
here
mental.
you drop all the 1 over m
So
operation.
this is in dot dot dot. So these are the pieces which survive in the m to infinity limit. No? And the reason why it happens that the dark matter mass, so I gave you one example. The other example is just technical. Now you see that the first operators you can write down, there's there's no dark matter mass, no? The 1 over scale which sits in here will come from the interaction, and the interaction is electroweak scale, right? So like this, maybe. So this comes from these exchanges, and the scale here is the Higgs mass and the W mass. Right? So these coefficients here are 1 over the electroweak scale. In this case, to the 3rd power. Makes sense?
Okay, can I ask a question just
Yes.
about the Higgs interactions? I'm just trying to think about the representations of like the products of the two triplets. You have two SU2 triplets, and then the Higgs is an SU2 doublet.
Oh, here.
Right. So is it the case that 3 bar cross 3 cross 2 gives you? Yeah.
Yeah, it's a good question. I don't have a good answer. I will have to go and look back at their paper, because there's was done. No, okay. So I think the answer is so they do many things. They also do doublets and triplets. So so several multiplets and the mixings.
Okay.
Yeah. So it's not just the Wino. So some of these diagrams will be 0 for the Wino.
Okay.
Yeah.
Okay.
But they do a more general matching.
Okay. All right.
Yeah, it's a great question. All right, so so the end result, so you get the scattering cross section. So what's shown here is as a function of mass of the Higgs. So we're here, and the reason why I'm showing this is that it highly depends on the Higgs mass. These two types of contributions from 1 loop and 2 loop cancel against each other, and the cancellation is almost perfect at leading order. But if we go to next to leading order, NNLO, NNNLO, you shift this this contribution, and you get a relatively precise prediction for the cross section. Right?
So what is NNNLO? QCD, what is this?
Yeah, okay, so their counting is a bit strange.
Sounds
Yeah,
scary.
there are too many n's actually. It's not a complete n cubed there. Yeah. All right, so I will switch. I think I have 10 minutes roughly. Yeah. All right, so there will be 2 topics, but it will be with a very broad brush. Right? So I think we're doing okay on time. So there will be another example of a special EFT, which will be the heavy dark matter annihilation, and then I will move to LHC. So let's say that we do the following. So let's say that we have a thermal Wino, and we want to calculate the annihilation to 2 photons. Thermal Wino means that this will fix the mass of the Wino to be at 3 TeV roughly. And then you want to measure the photon flux that comes from dark matter sitting, let's say, at the galactic center. It annihilates into photons, and you want to measure the photon flux, or it's above the galactic plane, in the dwarf galaxy, and so on. So this is an example where you need to use different theory tools depending on what you're actually measuring. So there are 3 different limits as to what you could possibly measure, and they are all characterized with how much of the initial energy is carried by the photon. So if the ratio between the photon and the dark matter mass, we'll call this Z. So we have dark matter, anti-dark matter, they annihilate, and let's say you end up with 2 photons. 2 photons and exactly 2 photons. So that means that the energy release was 2 times the mass of dark matter, and it went into 2 photons. So it meant that each of these 2 photons has the energy of m chi. and that means that the Z would be 1, no? In this case. So if you have an exclusive final state, the measurement is you take a Z and you cut a Z at 1, no? So you go at the very, very, very end of what Z could be. In your measurement, you go at the very last pin and you look at the photon, you see a line, and this would be a super precise measurement, and you know that it's only one photon. No? The meaning of only one photon means exactly this. No? You demand that it's the mass of this line, so the energy of this line is exactly the dark matter. Exactly means you have a super precise measurement. All right. So in this case, the prediction will give you there will be some Sudakov double logs because you're asking for only a photon. These are very high energies. The photons are electroweak objects. They will radiate like gluons at low energies. The same story. So they just split into E plus BB bar, TT bar, and then you radiate off a whole shower. And now you demand that this does not happen, and there's a penalty for this. This gives you this Sudakov log, and there are two because there are two legs. The incoming guys, so remember this dark matter is a triplet. It can exchange the W's. So the description of the incoming chi bar is captured by a non-relativistic dark matter, heavy dark matter effective theory that we just introduced with the W and Z exchanges. You need to resum these ladder diagrams, and this goes under the name of Sommerfeld enhancement, and it will give you bound states. All right? This is the same theory for all three types of measurements that you can do, so I won't show it on the left and the right. So let's move to these other options of what you could have. So one option would be that if I have a dark matter which sits here, no, annihilates, I dress it with the detector, no, and I measure fully inclusive final state. So I just measure any energy of the photon, so I pick a photon, the only thing I demand is a photon, and the rest is whatever, many Z's, many W's, BB bar, you name it, all the stuff that you can create with a 3TV object. So that means that Z cut here, Z cut, remember, is the energy of the photon, you put as low as possible. So you want to be completely inclusive. So that's one question you could ask, is an inclusive cross-section. It's just dark matter into anything. No? Now if you want to calculate that, it's a very, very different regime from asking just for two photons. And the tool that you can use is called an operator product expansion. What it means is that all this you can view as a forward scattering of dark matter, where you have a flow of very high momentum through a diagram, and it will match into a local theory. So that's why that's the operator product expansion. This means this, that you can use the fact that this is a very high scale to match onto local operators. Right? So it's what in words the technique. And then there's the third one, which is the most complicated. So now let's look also at this formula. So the Z, this Z variable, you can also write it in a different way. Instead of the photon energy, I can ask about the mass of this stuff in the final state, which is not a photon. So in this case, there is this jet of the photon you can barely see. It's called jet, the photon jet. And then there is a jet on the other side, plus a soft crab sitting around. So soft W's, and then a very collimated object, for instance, two W's shooting in one direction and a photon in the other. It's a very collimated object. And the mass squared of this object is given by 4 times the mass of dark matter, 1 minus Z. So when Z goes to 1, this will go to 0. this means that this object will be more and more collimated. No? The further apart they are, the bigger the invariant mass. So if they have angular separation, there is a bigger mass. If they're collimated, the invariant mass is small. All right? So if I dial z close to 1, you get a more and more collimated object. And this is called the endpoint region, where the z cut is close to 1, much closer. So this would be 1 minus z cut would be much less than 1, but is not 0. So we're not in the exclusive case. So here the tool is soft collinear effective theory. And alright, so of course it's the most complicated out of these three options is the one that corresponds to the measurements, has to be. So if you look at the Hess gamma line resolution, it's not perfect. No? It would correspond to a z-cut of about 0.2. So Hess is a telescope looking upwards for high energy gamma rays. And the photon line is this object. No, it's really not just one photon, but it's a range of photon energies that is allowed depending on what the mass of the jet on the other side is. So there is a variation of jets that you will sum over when you look for a line. No? So that's the cross section. It's not just a single photon plus another photon, but it's a single photon plus a photon and a Z and a W and so on. No? Alright, so this jet mass has a range. We're in the endpoint region. Formally you need to read some factors of log squared 1 minus Z. It's even more complicated, so that's denoted by the fact there are more colors here. And what's behind the scene is there are many scales that enter. So there's even SCT1, SCT2. So the resummation is both in the rapidity and the energy, and there are these different scales that are in between, and on top of it, it's also broken by the electroweak. Oh, it's a mess, no? It's really. So these are 80-page papers, but they're 80-page paper with a dense text, no? So it's quite an achievement. So what the end story is that if you look for, let's say, Wino with 2.9 TeV, this would be the prediction at leading log. Leading log, you just resum the logs at the leading order, and then the prediction next to leading log. So it seems to nicely converge. It's a function of z cut. So this would be the exclusive case. If you're sitting down there, it would give me an inclusive cross section. And the more exclusive I make it, the smaller the cross section, obviously. And this is where the Hess resolution is. So roughly, that's where roughly the cut is. You can also view it in a different way.
So the resolution is based on the z-cut. Is that just for this particular fixed mass? Or is
Yeah, I took it for 2.9. It ranges from 0.83 to 0.89.
Okay. So in reality, it's like an energy resolution.
Yeah, so if it's a 500 GV to a 10 TeV. I mean, the resolution changes and it translates to a slightly different z-cut.
Okay.
If you want it to be an exclusive case, this would need to be at 0.999, I think.
Okay.
So it's way off.
And Hess is better than Fermi-Lat or something like this?
Oh, so this is a 3 TeV. No?
Okay.
Yeah.
Okay, so it's super high energy.
Yeah.
Yeah, right.
Right.
That's
Anything else? So you can also convert this into a different thing. So that's the expected bound on the cross section from Hess with 250 hours of observation time and an isotope profile. And these are the predictions for the cross section. These lines. So this is the resonance structure, and this is where we were. That was shown on the other side. All right. So I have -1 minute, but it's really just pictures. I don't know if Pilar allows me to show 4 pictures. Okay, awesome. All right. So just wanted to show the following. So I talked about the EFTs. The EFTs break down where you have processes which are comparable with the mass of the mediator. And this will happen at the LHC. So the way you search for dark matter at the LHC is through monojet searches, where you have a dark matter that's emitted by a Z prime, and then you also emit a gluon in the p-bar collision. So this is a different plot that you usually see. Is not a log-log plot, but it's a linear plot. This is the background coming from the Z to neutrinos, and you want to see this deviation at the very tail. It's always the tail. So this is the usual thing. Now this signal from the linear plot looks huge. Now the question is, does dark matter EFT work at LHC? So let's say that we take exactly this model with a vector mediator, and you match it onto the effective operator, and you do the prediction for the vector mass of 500 GeV, and you see that really exactly in the region where you're sensitive to the signal is where the two lines diverge. So the EFT does not, so that the EFT, the red line, does not describe the true model. All right, so LHC processes is an example where you need to change. So the change is you build simplified models. So you just put in the stuff that you're missing, the mediator. So in our philosophy, the simplified models are also the EFTs. So you just keep the necessary ingredients. So this is a stolen slide from Uli Heisch that he stole from Martin Bauer. So it's a doubly stolen picture, but I think it's awesome. So in the early 2010s, you would describe the LHC results with an EFT. That was, of course, quickly realized, already this paper was shown, that, of course, it's just a Strawman model. It only works roughly. You really want to build simplified models. The first models were not electroweakly, had problems because you didn't really put in the electroweak gauge invariants, so you just need to build models which have electroweak gauge invariants, and that's it. So I conclude. What did I do? I covered the EFTs. There were two uses that I covered for the processes relevant to dark matter. I spent most of my time on this one, so parameterize our ignorance about dark matter interactions. However, I think moving forward, maybe it would become even more important that this is a theoretical tool that allows you to obtain reliable predictions for scattering or annihilation rates, and it will become important as soon as we discover dark matter. Thank you.